Hello, my name is Pradeep, and my paper is called Scaphy, Detecting Modern ICS Attacks by Correlating Behaviors in SCADA and Physical. We're going to go over a few topics: introduction, the process of Scaphy, existing work and how Scaphy is different, Scaphy's design, intent, and goals, a model called S3 model that they present in this paper, Scaphace implementation, some real-world evaluation, and finally some conclusion. Quick introduction of the background of this paper. Uh, Modern ICS attacks evade traditional monitoring tools like firewalls and or any network monitoring tools like SNMP based monitoring tools. Um, they can be launched from SCADA infrastructure, also called operational technology, and they target field devices and controllers like PLCs. Attackers can use legitimate ICS protocols. They could use like the regular Modbus or Ethernet IP, and they send commands directly to these field devices once they gain access to SCADA or the OT infrastructure. They can bypass basic protection measures like firewalls. They can send legitimate looking commands. While firewalls these days can block to certain extent, like stealth scans, they cannot detect protocol compliant ICS traffic. Let's say if there's a legitimate looking ICS traffic that is intending to change a set point or to start or stop equipment, firewalls may not be able to recognize that. One such example would be the Florida water treatment attack, where an attacker used a team viewer session. They gained access to an operator workstation and they increased the dosage for sodium hydroxide. And that would have created a dangerous process state. But fortunately, in that situation, the program was able to handle it and they had some alerting. Scaphy primarily detects attacks by correlating with the physical processes. Uh, While not entirely novel in the idea, more about that later, their work is somewhat new and it is commendable. This could result in identifying some new types of attacks that are otherwise undetected. The idea is that uh, typical looking SCADA activities, when performed in like an unexpected state, they might be able to indicate some anomalous states. For instance, let's take that example of the Florida water treatment attack. What if the sodium hydroxide level was already high, but if there was a set point to open a valve? So while the traffic from the SCADA might increase the set point, the physical state uh, somewhat deviates from that because it's already high. So what if you can model that and detect that as an anomaly? So that's kind of the approach of Scaphy, and they do this in a few steps. One of that is called the process dependency and impact graph, which identifies disruptive processes and like physical states. Uh, and they also do process-aware dynamic analysis, which, as I mentioned, like it differentiates legitimate versus abnormal-looking commands from SCADA. And in their test, they've achieved 95% detection accuracy of in a test bench scenario, and they had very few false positives across different industries. And they found that they're resilient to attacks where attackers might already know Scapy's approach. Scaphy process modeling. Scaphy treats SCADA as two different phases. One is the initialization phase, such as connecting to a field device like a PLC, doing OPC browse, which is reading the tag library. And the second is the process execution, which is normal commands sent during production states, such as changing set points, starting, stopping devices. Now, attackers' tools must also connect to the physical world, so they would also need to do this initialization, such as reading tags or opening sockets. So Scaphy analyzes traffic to see if such initialization behavior is observed during production or process control state. And they've also done some simulation where they trigger physical world changes at the PLC level on a test bench on a simulation environment using the OPC protocol and observe how the PLC reacts. So all of this is used to help create like a baseline for the legitimate process behavior. Scaphy does an iterative process of changing tag values on the simulation environment, and through this process, they accomplish a couple things. One is called the PDIG, which is Process Dependency and Impact Graph. It enables SCADA to assign each element an impact coefficient. Element is things like tanks or any process states. And another thing is called physics constraints. Physics constraints is what is considered normal process and what is within bounds. And as Scaphy toggles these elements in the simulation environment, they record uh, what they call API calls, or in other words, SCADA actions, and they establish these physical constraints. This physical model detects when control signals drive a process outside the set point range or into like a deviation state. By correlating SCADA commands with physical states, Scaphy provides contextual alerts to operators. They're able to limit the attacker's operations by detecting anomalous behavior in unexpected operation phases. And as a result, they're able to detect modern ICS attacks by using different tools. So let's say a situation where an attacker gains access to a circuit breaker or an actuator. Um, they're able to recognize that by monitoring the physical level in addition to SCADA actions. Some of the limitations of the existing work are that they focus extensively on the network traffic analysis. In some cases, they also look at the physical models, but uh, often they don't work together, which means there can be higher false positives. Traffic analysis might be able to detect abnormal flows, but they may not be able to know legitimate traffic, uh, such as like let's say an abnormal change of set points. Existing physical models might use linear or autoregressive methods that'll require a lot of expertise to build. Where Scaphy might be advantageous is that they monitor SCADA's execution phases and they're able to flag API calls or SCADA commands that occur in atypical phases, such as, once again, changing set points when, uh, let's say, like try and increase valve output when, let's say, a tank is already full. Because they're able to correlate physical states with network traffic, they're able to better recognize and have a better context with all SCADA commands. And they're also able to observe all the traffic from the VM host so they can catch hidden attacks. And they're using Windows kernel patch protection to detect rootkits that could be injected into the VM. And overall, they're able to reduce false positives that may be, missed by traditional tools. Looks at the OPC tag dictionary and the function block diagram PLC programs, and it outputs two things: the physical model, also called the PDIG, and the physics constraints. The PDIG, it assigns impact scores to element states to detect disruptive signals, whereas physics constraints are those that are not that are to be followed at all times. They can differentiate normal activity versus attacker activity. And how they deploy it is they have it on the VM host. In this case, they use XCP-ng as the hypervisor, so they install it at the hypervisor level. They monitor the network interface for SCADA control signals that will change element state. They can do this by inspecting the ICS protocols, many of which are unencrypted, uh, oftentimes easily recognized by most software like Wireshark, for example. Uh, Network analysis software can differentiate, like let's say Modbus read registers versus write registers. So they're able to inspect these protocols and analyze traffic. Scaphy's analysis and detection workflow. Scaphy, more on that simulation. Scaphy parses these ICS scenarios to analyze and partition ICS elements into terminal and non-terminal sets based on heuristics from OPC. Terminal elements identifies processes like tank level control. Scaphy then traces each element's connections to map physical process or element dependencies. Scaphy loads these scenarios into an ICS engine. They do that using control IO, and they perform a physical process aware dynamic analysis. Essentially what it is it's a simulation environment where they change the element states, that is by changing tags, and they establish this so-called physics constraints. The change in process output caused by each state switching is averaged over several PLC scan cycles to derive an impact score for each state relative to others. For states with oscillating impact, where the process output may increase in some situations and decrease in others, Scaffold derives a set point range or a normal operating range, which defines a minimum and maximum impact score for the processes. Scaffold raises alarms when executed APIs in the process control phase are not within the physics constraints, and when control signals causes inconsistent state or set point deviations, and when, let's say, out of order commands are seen from SCADA. Scaffold, using all of this, computes an anomaly score to prioritize alerts. Diving into the system design, part one is the automated physical process comprehension, and as part of that, they extract the OPC tags from the tag library, and they'll also look at OPC alarms and events. Using that information, they're able to observe the possible states of each tag. So let's say if it's a Boolean tag versus an analog tag, they're able to identify the process, and also by looking at the tag names. So now each process is mapped as a sensor and the terminal element combination. A sensor could be a level sensor, and tank would be the terminal element in the case of, let's say, tank level control. They consider all other processes as non-terminal, and they map these dependency sets where each dependency set would be a bunch of terminal and non-terminal processes that have dependencies with each other. And essentially, the PLC logic is represented as dependency path top tuples per process within the logic. Modeling. Sketching the PD graph is it involves a map that is made of nodes representing the system parts and edges showing relationship between these parts. Some connections between nodes have a direction showing an order of operation, and others are undirected if there is no required sequence. Each node is labeled with potential states and an impact score, so you know both what changes are possible and how much they matter. Scaphy marks special instances where an undirected edge goes from a terminal one to a non-terminal element, highlighting process transitions within the system. How does Scaphy monitor the impact of changes? It does that by giving each device or system a score called impact coefficient. This score shows how much changing the state affects the whole process compared to other possible states. When something changes in the system, Scaphy checks the score to tell if it's a minor shift or something that can signal an abnormal event. Unimportant states with low scores get ignored. This means that Scaphy only monitors what actually matters. Scaphy doesn't compare combinations of different states together. It just looks at the impact of each state by itself. So the analysis stays simple and understandable. The scoring starts with all devices set to the same starting point, and if any state is switched, it is tracked until the system behavior settles down. The impact scores are adjusted so that they fall between 0 and 1, making it clear which states are most important. This approach helps identify meaningful changes. It avoids wasting attention on insignificant processes. It also keeps the monitoring system simple and understandable. In this paper, they introduce a model called the S cubed model, where they characterize the internal layers of SCADA infrastructure and communications into 5 different layers. It has some parallels with the Purdue reference model. In fact, it expands the Purdue layer 1 and 2 into 5 layers. With the S cube model, we have the first or the S0 layer, which is the real hardware like sensors and actuators, and the S1 model is the ICS drivers, the talk to field devices such as let's say Modbus TCP, Ethernet IP. The next one is the device object layer, the OS handles that represent these devices, let's say sockets for specific uh, PLCs. Then the access or callback layers. These would be the APIs that or protocols that SCADA uses. Let's say Modbus read register command or write register command. And then the SCADA application layer, which is the HMI graphics and such. More about the S3 model and why it might be useful. Now, within the S3 model, these layers indicate how communication might flow. Could you use that information to maybe see anomalous behavior? What if you see information like or commands like OPC browse when the under like production states? How can the S3 model help? So they look at the execution in 2 phases, as I mentioned. One would be the setup, like initialization, opening the sockets, OPC tag browse, and the other one is the process control. And so using the PDIG, they, they're able to compare and analyze with the S3 model when traffic looks out of order or abnormal for the current process control phase. And they also use virtual machine introspection to observe host behavior, and they can follow the expected S3 layers, and as I mentioned, they can see when the timing of certain actions are not right to indicate an anomaly or an attack. So by adding semantic context to legitimate looking protocols like just simple read write commands, they're able to see who is sending this, when, like what state of the process they're sending, and even like why as process field states change. They're able to add context of who, how, and when. And this can help indicate a cyber event that may not otherwise be found by, like simply monitoring the traffic. Scaphy's implementation, kind of recapping what's been said so far. Scaphy leverages the S cubed model, which breaks down the Purdue Level 2 into 5 layers. This allows precise tracking of all traffic at each layer as it goes to the physical world. And SCADA also uses these functions like create file, read file to talk to devices. Malware might also use these handles, and Scaphy monitors them. Um, Scaphy also identifies process control phases. It'll know initialization versus process control execution. It'll track Ethernet IP registers, Modbus registers, and it'll know when. It'll also observe loop completions and time. How did the authors implement uh, Scaphy to accomplish the two goals, which is the physical process aware analysis that generates the PDIG and the physics constraints? They've used Factory IO to emulate the process, and they used Siemens Step 7 SCADA software for testing. They've captured APIs that tie to real physical actions using OPC data, and they've produced physics constraints that'll show what legitimate API calls are. So that way they can whitelist those actions. And right, physics constraints, these are these whitelisted legitimate API calls. They make detection process aware. They're able to detect injection violations. That is when new unlisted APIs are injected, and then bypass violations. Let's say when a rootkit or a kernel entity sends signals directly to the hardware, skipping the necessary S cube layers, which is S2 and S3 in this case. It also detects stealthy ICS malware that might be missed uh, by just whitelisting traffic using the host IP and ports using this process. Scaphy was evaluated to see how well it performs in comparison with existing ICS protection tools. It was tested on 40 different simulated attacks across 24 ICS scenarios in four industries using both SCADA and physical systems in a US National Lab test bench. The platforms that they've used are Siemens S7, WinSPS SCADA, and MySCADA, and Factory IO for the simulated PLC simulation. The results that they found were 95% detection rate of well-known real malware such as Havix and Destroyer, 3.5% false positives, and they've accurately tracked behavior across all five S3 layers. They've tested four different attack categories: altering process states, blocking SCADA access, data collection attacks such as reconnaissance attacks, and then exploiting device bugs. And they've been successful in all of these categories. A couple different case studies in how Scaphy performed. Ukrainian power grid attack, the in destroyer malware. Just to summarize, what happened with this attack was some attackers got access to a Siemens breaker protection equipment. They managed to get the exact tag, like the Boolean tag, to close the breaker or open the breaker, and they've opened the breaker, so it kind of cut off that line. So Scafie detected this because it saw that there was an abnormal API in the wrong phase. So that's step one, the physics violation, and step two is the physical state conflict. Normally, you would expect the PLC to close the breaker, knowing that there's an imbalance in the load, but that didn't happen, meaning there's a conflict that's caused by this external bug or malware that opened the breaker. And Scafie detected both of these in less than 9 seconds. Case study two is the Florida water treatment attack. They have detected the abnormal sodium hydroxide dosing and valve behavior. They caught inconsistency between the tank level and the valve states. They saw that, let's say, the tank already had high dosing, but the valve for the sodium hydroxide was still open. So this was seen as a physical state conflict, and Scafie detected that. So, and Scafie overall outperformed trial models using sensor analysis and network traffic classification. So models that use these two techniques. It achieved higher accuracy and fewer false alarms by using or correlating the SCADA actions with physical world changes, physical world context. Advantages are that by using the physics constraints, it is able to whitelist what it calls SCADA API actions or SCADA commands that are considered normal for a specific state of the process. By combining software behavior and physical process logic, they're able to detect attacks that might look normal to a firewall. This is the biggest strength of Scafy, but some of the limitations of Scafy is that emulating this the state switching, like in order to even get this PDIG model and the physics constraints, it needs an entire digital twin to be able to simulate and create these tag changes and observe the states. In large plants, this might be quite challenging. And ICS attack development difficulty. Creating unknown attacks is another challenge because a lot of SCADA software are very proprietary. They're not open source. So knowing how reliable this would be, Scaphy would be for unknown zero-day attacks is hard to predict because less resources are available. And as I mentioned earlier, like modeling these physics constraints can be quite challenging because you need the digital twin. And it also doesn't detect side channel attacks that is outside the scope of this paper. And it doesn't detect attacks originating out of SCADA host stack. So let's say there are some attacks that might come from the same subnet, not necessarily from the same like same host. So SCADA may not, like Scaphy may not be able to recognize these attacks. I've been in the SCADA, ICS security and operational technology industry for little over 9 years, and this slide is about my opinions as an industry insider. One of the issues that I find with Scaphy is a lack of information, especially with how SCADA software operates. Rarely is there any control logic or process logic at the SCADA layer. Almost always is the process logic is at the PLC or your RTAX and DCS. So SCADA in pretty much every industrial case is merely a read write to the tags within the PLC, but it's not actually doing any process control. Like there's no PID logic at the SCADA layer, unlike what the paper suggests. This can be an issue for Scaphy to work or be any more effective than existing products because not always is an action from the SCADA host anomalous without using an external malware, right? So if there was an external malware, it would open its own TCP socket, and in many cases, it's recognized by, uh, any modern endpoint protection software. And the Indestroyer attack in Ukraine that this paper extensively refers was also a malware. So it opened its own TCP socket and it would have been recognized by majority of existing ICS protection software. But that said, Scaphy would have successfully detected the infamous Stuxnet attack, which used legitimate Siemens software. It used a bug in that software, but Scaphy would have recognized it because it can see OPC browse as a separate state. That's the initialization state. And however, I think this attack would have also been identified by a combination of deep packet inspection firewalls and or any modern application control capable endpoint protection software. One of the other challenges is that building a physical model using PLC code. Programs are not always written in one language, definitely not always in function block diagram. It's a combination sometimes. And even if a standard was used, it would be quite challenging to build a model, especially in factories and plants that use multiple PLCs to control multiple sub-processes that are dependent. Such as in a water treatment plant, there's multiple processes that have links. Some of the things are running in manual, some of the elements are in auto. It would be quite unpredictable, and it would be very challenging to build a model. It remains to be seen how effective Scafé would be in such a plant like that. If uh, if it's not effective enough, it might just be one more software to fill the sim event logger, and it'll be eventually disabled. Uh, however, the most important thing is correlation. Correlation should be studied further. I think it is an excellent, outstanding, novel approach. I think it has the potential to protect from zero day vulnerabilities that show up in the SCADA environment. Um, I view Scafy as a complement to endpoint protection, but it's not a replacement to any of the existing OT security measures, in my humble opinion. However, it has the potential to augment existing security measures such as endpoint protection with application whitelisting, firewalls with deep packet inspection, least privilege and least function based access control, segregation of networks and restriction of information flow, zero trust based security, defense in depth, and islanding critical and safety networks. That said, Scafy does remind me of a company that's currently out there. It's called Sega Security. It's a German company. They actually do this process. They monitor the physical states of hardware, but they do that by adding a secondary channel. Let's say they add a 4 to 20 milliamp splitter to monitor the sensors directly, and they also do compare the PLCs, and they build machine learning models to do this overall analysis with correlation.